All right, so I'm going to call this example 1. And we're actually going to do like, I don't know, I guess probably 2 or 3 things in this. And so I want you to not just pay attention to the equations. All right. All right. That's the easy part. All right. What you really need to focus on when you're doing problems in special relativity, as we're doing them here, is to figure out when there's an observer seeing an event. Okay. In other words, someone making a measurement of something. When the observer sees an event, are they witnessing a proper length or are they witnessing a proper time? And it could be neither. All right. So we talked about in our lecture how proper length and proper time are very specific measurements. Doesn't mean correct. It just means one specific kind of measurement amongst an infinite number of potentially correct measurements. Okay. So we got to dispense with the idea of right measurement and wrong measurement. In a way. Okay. So there are these particles called muons, and we're going to talk about those more later on. But for now, just kind of imagine it's not an electron, it's not a neutron or a proton. Think about it as something in between. Okay. And these are created high in the atmosphere when cosmic rays coming in from either the sun or distant stars. They collide with nuclei, and then the muons are created as a result of that. Okay. Now, some of those processes we're going to talk about later on. Okay. But for now, let's just suppose that we have a muon up here in the sky. Okay. And we use mu to signify that. All right, and that particle's got a certain mass, and that's not relevant for what we're doing now. But when these particles are created, they have a lot of kinetic energy. Okay, I mean a lot of kinetic energy, and they move really, really quickly. Okay, in fact, the velocity for these things is going to be around 0.99996 times the speed of light. Okay. Now, if you want to convert that into meters per second, that's fine. Go ahead. All right. You're just going to get a big number that's going to be difficult to deal with. All right. And in relativity, we often deal with things as a percentage of the speed of light, okay, as a fraction of the speed of light. So 99.96% of the speed of light. All right, so these guys are booking it, okay. They are really cruising, all right. And they're headed down towards the Earth, okay. So down here is the Earth. All right. And most of these, where they're created, they end up traveling a distance here of around 15 kilometers. Or, sorry, that's not right. Yeah, I guess it is right. Okay. Yeah, 15,000 meters. Yeah, okay. Sorry, got confused there for a second with myself. Just like that. Okay. So about 15 kilometers. All right. And so then they got to travel this whole long ways here. Okay. And we want to ask some questions like, well, how long does it actually take them to travel this distance? Okay. And that's that sort of thing. So actually, let's start with that question right there. Okay. How long does it take for them to travel that distance? Okay. So their velocity is just going to be the length divided by the amount of time. Okay, so we know that. That's pretty elementary, right? Okay, so we got length over some transit time like that. And so if we just take our length and divide it by our velocity, we're in good shape. So we could go here 15 thousand meters. And we're going to divide it by 0.9996. And now on your calculator, this is a good time to put in the speed of light here. 2.998 times 10 to the 8th. And a lot of you probably have noticed I'm using 4 sig figs here instead of 3. Okay, so it turns out that the faster and faster you go towards the speed of light, all those extra digits can make a big difference. Okay, they can make a really big difference. I'll try to illustrate that in a little bit. So anyway, once we do this, we get a delta t here, our transit time, which is 50.05 microseconds. Okay, just that. Okay. Okay, but now what we've learned, though, so far is that lengths and time measurements can vary depending on who's making that measurement. Okay, so let's step back. We got these two measurements here. We've got a measurement of length. We've got a measurement of time. And let's consider if one of them is proper, or maybe they're both proper, or maybe neither is proper. Okay. So let's start with the length. Okay, so the length, is that a proper length? So in order for it to be a proper length, okay, then that means, oops, let me redo that there. Okay, so proper length, okay, means it's time independent. Okay, so it doesn't, whatever answer we get there doesn't depend on time. So can someone measure that 15,000 meters of atmosphere independent of time? Well, the answer is yes. Okay, you can do that. All right, and so there's different ways to do it. It doesn't really matter what those ways are. The point is you can do it. Okay, and that means that distance there is my proper distance. Okay. Now, one of the things to keep in mind is nobody gets both. Nobody can measure both proper time and proper distance for any event. Okay, you get one or you get the other, but most of the time you don't get either one of those. All right, but in this case, we can get the proper length, but that means then it's not the proper time. Okay, so if we could sit along with the muon, all right, and experience what the muon sits, we might say, how long did it seem like the muon traveled from the muon's perspective? And how far was it from the muon's perspective? Okay, how much time did it take? How far was it from the muon's perspective? So what I'm going to do is I'm going to go back and I'm going to change my notation just a little bit. Because this length here, that is kind of an Earth-centric length, all right? That's the length measured on Earth. And then this time here also is the time measured for Earth, okay, for people standing on the ground. We need to get that for the muon, all right? Now, so what happens, the length for the muon is it sees a compressed distance, okay, a compressed distance. And the way that we do that is we're going to take the length for Earth and we're going to divide it by our Lorentz factor, gamma, okay? Gamma is the Lorentz factor. So that means we actually we need to pause and calculate gamma and then come back to get that. Okay, so gamma is 1 over the square root of 1 minus beta squared. Okay, now keep in mind that beta is actually V over C. It's a ratio. So in our particular case here, beta is that ratio we started with, 0.9996. Okay, just like that. Now, if you go through the calculation, I'm not going to take the time to do it here. You guys are competent with your calculators now. You can plug that number in. You can work it out. But what we get for gamma here, once we plug beta in, is we get, looks like 3536. Okay. And so that's our Lorentz factor. Okay. All right. So now let's use that. Let's plug that back in. All right. So we come back to our working relationship here. So the length of the Earth is 15,000 meters. Okay. And then the Lorentz factor is 3536. Okay. And once you do that computation, okay, work that out, what you get is 424.2. Okay. Trying to stay with 4 sig figs here. Considerably shorter. Okay. Considerably shorter. All right. 15 kilometers versus basically 5 football fields. Okay. So what the muon experiences is quite a bit different. Okay. So that's how far it seems to the muon. Okay. Now, what we need to ask ourselves now is, the Earth people obviously can't measure the proper time because they're measuring proper length. On board, the muon, is that going to be a measurement of proper time or not? Okay. So here's how we think about this. All right. Let's imagine, let me come over here just a little bit. Let's imagine there's a little tiny window, boop, on board the muon, and we got somebody traveling inside there like it's a super teeny tiny spaceship. Okay. And when the muon's first created, all right, the people inside, whoever's inside there, they open this window and they're like, huh. And they close it right back up immediately. Okay. But they can see where they are. Huh. Okay. Then once it reaches the ground, okay, sometime later, all right, we don't know what that time is yet, but sometime later, they open the window again, oh, and they're on the ground. Okay, so to them, all right, they started here, they're here, Earth is moving up towards them, okay? They're poof, they popped into existence, now Earth is coming up at them, all right? But what happens is, they look, they don't think they've gone anywhere. But the scenery outside the window has changed. And they can measure how much time it took for that change of scenery to happen. Okay. And so since they didn't go anywhere when they made their time measurement, then that means that their measurement of time doesn't depend on distance. Okay. And since there's no dependence on distance there, then that makes that a proper time. Okay. So in the muon there, the time they experience is the proper time for the muon to get from way up in the air down to below. So the relationship between a proper time and every other time is also connected by the gamma. Okay. And so it usually works. We usually say it like this. All right. We say that every other time. So in this case, the time for the Earth is gamma times the proper time, like this. Okay. Now notice they're a little bit different. Okay. So you got to always picture in mind, you know, are you having contraction, length contraction, or are you having time dilation? Okay. Which way is it going? Okay. So, anyway, let's get on with it here. So then we're going to have delta t for mu, okay, is going to be delta t is seen on the Earth. And we're going to divide that by gamma like this. So now we're looking at 50.05 microseconds divided by that same Lorentz factor, 35.36, and the time that the muon experiences then is considerably shorter, 1.416 microseconds. Okay. sort of like that. All right. Now, there's no shortcuts here. Okay. You may be tempted to be like, okay, I just got to remember this, or I just got to remember that. Okay. There's no shortcuts like that. You're always going to have to think through, do you have proper time or proper length for either party? Okay. For either party. If you can identify proper time or proper length, that's great. Okay. You've just made huge progress. All right. We aren't going to be dealing with situations where you might not have proper time or proper length. Okay, I'm just going to tell you that right now. In order to deal with that, you need a whole different set of tools called the Lorentz Transformations. Okay, and we just don't have time to get into it. They're not difficult, but we just don't have the time to get into that. Okay. So there you go. All right. So there's kind of a fun example with some numbers there, looking at how different lengths are experienced and how different times are experienced. Okay. So a lot of your homework is going to center on this kind of thing right here. Okay. So hopefully this example will help you out a lot. Okay.